Rightio, so we had a look at this one on the graphing program, and saw the answer looked to be maybe somewhere around about 2, and we're now going to have a go at doing it properly. So here's our function. It's a parametric function, so theta is the parameter. We've got the x and the y, so if you're not sure how to do parametric differentiation, go back and have a look at the pre-calculus review stuff that's on Moodle, and it shows you how to do it. But basically, you need to differentiate the two parts separately, so dx by d theta is 1 minus cos theta, derivative of this thing, and then we differentiate the y as well, so dy by dx is 1 differentiates to 0, minus cos goes to sine, so it's just sine theta, and the parametric differentiation is that dy by dx is dy by d theta times d theta by dx, so it's going to be dy by d theta is sine theta, and d theta by dx is 1 over this thing, so it's going to be over 1 minus cos theta. Okay, so that's our derivative, and if we evaluate that at theta equals pi upon 3, so we just stick pi over 3 into this equation and push some buttons on the calculator, comes out to be root 3, or 1.732 is the way the calculator will tell you, but root 3 is the actual value. Okay, so that gives us dy by dx, and so we can use our radius formula, remembering that the radius formula is 1 plus dy by dx squared to the power of 3 over 2 all over the second derivative. We're going to need the second derivative of this equation, so I have to differentiate this thing again, so I've got dy by dx, and I need to differentiate it again, and the second derivative parametrically is dy by dx squared is the derivative of the first derivative, obviously. So what it normally is, so in this case it's d by dx of sine theta over 1 minus cos theta. That was our first derivative, but that's a theta, so we can't differentiate it dx, but I can differentiate it d theta. Again, this is all on the pre-introductory thing, if you want to have a look through that. And now I've changed the variable from x to theta. I need put a change in for that, and now I can just do this. So this is a quotient rule, so it's the derivative of the top one times the bottom one minus the top one times the derivative of the bottom one all over the bottom one squared times d theta by dx, which is the same as 1 over dx by d theta. Okay, so that's my expression for the second derivative, and I could spend some time trying to simplify that if I wanted to, or I could just evaluate it. So let's just pretend I'm going to evaluate. Well, I am going to evaluate it. So at theta equals pi over 3, so I'm just going to stick pi over 3 into this equation here, and if you do that, you'll find the answer comes out to be negative 4. So the radius of curvature is 1 plus the first derivative squared all to the power of 3 over 2 divided by the second derivative. And if you evaluate that, you'll find it comes out to be exactly negative 2. Okay, so the radius of curvature in this case is negative 2. So the 2 is the important bit, it's the size of it, so the radius of the circle, it just fits inside the curve, is 2. The negative means effectively it's below the curve, but we'll do that when we come to locating the centre of curvature. So the radius is 2 units. Okay, and the negative sign is important, and we'll use it shortly.